Daniele Steer from APC Airs.
Yes, I'm sorry, I'm not Anne Davis. And I'd also like to say that I think many speakers have touched upon what I'm going to talk about, so I hope there's not too much repetition for you. So if you get bored, I'm sorry. So I'd like to try and explain what I think is the influence of Y junctions on the evolution of a string network, and also the important role which I think kinks may play in these networks with junctions. So in the previous talk we heard about different types of junctions, X junctions, Y junctions and other. So I'm really focusing on Y junctions. Why? Because they look like a Y. I mean, that's why they're called Y, because they're a Y shape. And they typically occur when two strings meet and form a bound state. And that's very characteristic of cosmic superstring networks. So I'm going to talk about essentially two things which are related, which I've done with collaborators in Paris, so Pierre Binetruy, Alex Boy and Thomas Hertog, and with collaborators here in the UK, so including Le Bon, of course, who spoke earlier. And the first part of my talk follows on from what he said. So Le Bon already showed this plot in his talk, so it's a plot of GS against mu F. So these are two fundamental unknown parameters of superstring theory, so extremely high energy physics, whose values we don't know. But the interest is that in these models of superstring motivated inflation, so inflation motivated, well, in deep brain inflation, superstrings are formed at the end of inflation. Their properties depend on these two unknown parameters, but strings leave observational consequences. So if we can measure those consequences, then in principle, at least if we have two different measurements which constrain different combinations of the parameters mu F and GS, then in principle we might be able to get a handle on these two unknown parameters of superstring theory. So that's the hope. So Le Bon, as I said, presented this. This is a constraint coming from CMB physics, and this is a constraint coming from gravitational wave physics. So I'll talk a little bit about the properties of individual strings and the evolution of a tangle of strings with junctions, or how it might go. So the second thing I want to talk about is kinks, kink proliferation in particular. So if you imagine that you're playing with your children and each of them has three strings which are attached at a junction, if you send in a wave towards the junction, which in this case is two kinks, the two kinks will be transmitted on each of the strings, so there'll be two on each of the string, and there'll be a reflected wave. So one of the characteristics of string networks with junctions, it seems to me that as soon as you have kinks propagating towards a junction, which you always will have, then the number of kinks will increase. So kinks proliferate. And in particular, if you have a closed loop of string, then you can imagine that as three strings, well, as one of the kinks propagates along here, produces three that go right back around to the beginning, etc. So the number of these kinks is very large, or can be very large. Now, as Tanmay and Alex Valenkin pointed out a long time ago, kinks are sources of high frequency gravitational wave bursts. So these short bursts of gravitational waves, which you can imagine a bit as being like a short burst of light coming from the Eiffel Tower if you're looking at it in the right direction at night. And so, as Damour and Valenkin pointed out about 10 years ago, if an observer or experiment lies in the direction of one of those gravitational wave bursts, then you would see a stronger than usual gravitational wave amplitude, and that might be a way of observing strings. So the second point essentially is that string networks with junctions presumably have more kinks because they're reflected and transmitted when they hit a junction. These radiate gravitational wave bursts, so would there be more gravitational wave bursts from a network of strings with junctions? But let me go to the first part, which was on the evolution of strings with junctions. So as many people have pointed out, the characteristic feature of these networks is that there's a whole spectrum of strings with different tensions. Now, in fact, the precise expression for those tensions depends on the string theory model. We looked at the simplest one. So as we heard earlier, there are two parameters. So mu F fixes the overall normalization of the tensions, so it's in scale. And then there's this string coupling GS, which takes values between 0 and 1. And the strings are labeled by integer numbers pi and qi, which you can think of as labeling the fluxes on those strings. So each string is charged under a different field. And so the lightest string has p equals 1 and q equals 0, so it has tension mu f. The next lightest one has p equals 0 and q equals 1, so it has a larger tension because gs is between 0 and 1. Then the next one has p equals 1 and q equals 1, and it actually has a lower tension than each of these two individually. So what happens is that when, for example, a 1-0 string and a 0-1 string meet, they form a band state of a 1-1 string. Now, of course, you also have to impose charge conservation at the junction, so that the sum of the p is 0 and the sum of the q equals 0. And there are band states at all for different values of these integers pi and qi. Okay, so if you want to model how a network evolves, you also need to know the dynamics of these strings. So they're simply described by the Nambu-Goto action. There are no long-range interactions between the strings. In fact, it's slightly more tricky. You need the Nambu-Goto action for 3 strings, plus the constraint that they actually meet at the same point, because if not, you wouldn't be modeling a junction. But that's not too difficult to write down. And it's a completely deterministic system. If I give you the initial conditions, then you can find the position of the string at all times. So here's an example of a rather simplistic loop, which has a certain number of kinks at the initial time, and this is how the thing evolves with time. And I stopped it at some particular point. It's not very clear from this diagram because of perspective, but the number of kinks does indeed increase, as I mentioned earlier. The kinematic constraints have also been mentioned this morning. So from the equations of motion, you can actually more or less work out what happens as a result of a collision between these strings. Because the strings are charged, they cannot reconnect. That's contrary to charge conservation. So either they go through each other, or they can form a bridge with 2 junctions in different directions. And using the Nambu-Goto equations of motion with as initial condition 2 straight strings moving towards each other with velocities v and minus v at an angle alpha, you can work out exactly in which region of parameter space is the reconnection, for example, along the x, so what I called an x-link, where the middle link is horizontal. You can work out precisely for which values of alpha and v, the relative velocity, an x-link is allowed. So that's just kinematics. The constraint comes from saying that if this link is going to form, then its length has to increase in time. That's the only place, that's where it comes from. So the length of the link increasing with time is this boundary here. So links in the x direction can form when the velocity of the strings is low and when the angles between them is small. The opposite link can form for large angles and for, again, low velocities. If the velocities are high, the strings tend to go through each other. So we actually checked this in an analog model, or at least in a field theory model, which has Y junctions, which is the U1 model deep in the type 1 regime, which Anna mentioned this morning. In fact, this work is with Anna. So in this, of course, the standard abelian-Higgs model in the type 1 regime, you have winding 1 vortices and winding 2 vortices, and the winding 2 vortices are a band state of winding 1 vortices. So if you fire 2 winding 1 vortices together, they can form 2 junctions and a winding 2 vortex in the middle. And so we did this simulation, and we showed that in the dynamic, or in the kinematically allowed region, which comes from the previous transparency, so where junctions can form and links can form, in fact, dynamically they do form. And in fact, the boundary follows very well the theoretical boundary. When the junctions can't form, then the strings, in this case, intercommute, which they can, but for cosmic superstrings they can't because they're charged. Okay, then we need to go to network evolution, which again has been mentioned this morning. And in fact, you can do quite a lot without writing down any equations of motion, apart from the Nambu-Goto equations at the junction. The reason is that a network will contain many junctions randomly orientated. So we can just average over all the junctions in the network, assuming they're randomly orientated, and use the local Nambu-Goto equations to understand the dynamics at the junction. So you can ask, for example, how fast on average the junctions move along a string of tension mu I. So this is the average rate of increase of length on string of type I as a function of GS, which gives you the relative tension between the different types of string. So as you can see, the lightest string, the length of the lightest string, the F string, or the 1, 0 string, is always increasing for all values of GS, whereas the length of the heaviest string, on average, always decreases. The length of the D string depends on the value of GS. So the tendency is always for lighter strings to grow at the expense of heavier ones. And so, for example, if you look at small GS, where the D string is much heavier than the F string, the length of these doesn't change. They're infinitely heavy, so their length doesn't change. There are presumably few of them, but as Levon said, they're so much heavier, maybe they dominate the energy density, so they're fewer in number. Okay, so we're going to come to that point in a minute. The last thing we needed for the work with Levon on the evolution of the network was the probability of intercommuting of two strings. So the probability of string I interacting with string J. So Anna mentioned that probability in the cosmic superstrings is in fact a quantum process. So strings actually can explore the extra dimensions, so there's a chance of them missing each other in the extra dimensions. And this process which is calculated in these two papers, depends on GS, so one of the two fundamental parameters. And it also depends on the volume of the extra dimensions and the volume explored by the strings in the extra dimension, which for us was a new parameter, which we called W, which we varied between 0 and 1. In fact, it's a ratio of volumes that can go between 0 and 1. And we lifted these quantities from the different papers that have calculated them. So I just want to indicate that there's a GS dependence. If an F string interacts with an F string, this probability depends on GS squared. If an F string interacting with a G string, it depends on GS. So with all of these things, we could go and try and understand the network evolution. And we used the velocity one-scale model, dependent one-scale model, which Paul presented this morning, we heard about in the previous talk. And we extended along the lines that have been done by other people, so in particular Denis-Diderot and Copeland, to include the effects of strings of different tensions meeting at Y junctions. So if we've had the variables of the correlation length defined by the infinite string density, and the root mean square velocity, and there's one for each string of type I. Okay, so I again labels a different string. And the density in string of type I changes for a number of different reasons. It changes because of the expansion of the universe, because of redshift. It changes because strings chop off loops of type I. So this parameter C is related to the efficiency of loop formation of type I. So I do want to stress that this does not include any loops which may have junctions in them. So it only includes the effects of chopping loops of one color, let's say. I'd like to think of them in terms of color. And this parameter will depend on the intercommuting probability, which I discussed on the previous transparency. So it's a function of GF. Then there's another term, which is a removal of energy density in string of type I. So energy or length in string of type I is removed when the string of type I intercommutes with another string, producing a junction and a link between the two. So that's what's included in this term. So this removes strings of type I when a string interacts with a string of type A and produces a link of type K. And that will depend on the intercommuting properties, again, which I discussed. It depends on the kinematic constraints, and it depends on the velocities at which these strings are colliding. And finally, there's the converse term, which produces strings of type I as a result of collision. So this is a complicated equation, which should be solved with another equation for the root mean square velocity. It's a closed system, which we solve, with the aim of getting the GS dependent, as Levon pointed out before. And so as we've heard now a number of times this morning, these networks scale. So the correlation length over time is a constant. And I won't go through this again, but Levon pointed out how these different parameters, this one, which is this is the number, essentially the number of density of strings, how it depends on GS. The lighter strings always dominate, and how the energy density, which fixes the overall amplitude of the CMB power spectra, depends on GS. And as he said, the F strings can dominate at large GS. Okay, let me go on quickly to the second part of my talk, which is on kink proliferation, in 5 minutes. Yeah, 4 minutes. Okay. Okay, so kinks are sources of high energy, of high frequency gravitational waves. That's just a consequence of the Einstein equation. So this is a linearized Einstein equation. The transverse traceless part, so this is omega, the frequency of the gravitational wave, and this is the stress energy tensor of the string, which is sourcing the gravitational wave. And as I said, as Tanmay and others have shown, a cusp will emit a gravitational wave with amplitude that decays as 1 over, or frequency to the minus 4/3, whereas a kink emits a gravitational wave whose amplitude goes as frequency to the minus 5/3. So at high frequency, this is a less strong effect than the effect coming from cusps. But on the other hand, there are more kinks. Now, the other thing which is important is that the gravitational wave emitted, its amplitude also depends on the sharpness of the kink. So maybe you might think that when these kinks come into a junction and are reflected and transmitted, the sharpness somehow goes down. But in fact, that's not the case. There's no simple conservation law for kink sharpness when they go through a junction. Okay, so kinks emit gravitational waves. In fact, the junction itself, as you can see, it moves sharply when a kink goes through. It also emits gravitational waves, a burst of them. But it's a stronger effect. It goes as one. It's a less important effect. It goes as 1 over omega squared. So we just focused on the kinks at the moment. So as I said, kinks, when they propagate towards a junction, they multiply. So the number of kinks increases exponentially, and in fact the number of very sharp kinks also increases exponentially. And we've tried to simulate these loops, at least as realistically as we can, and we've shown that the typical number of kinks can increase really as large as 10 to the 6th at the end of a simulation, at the end of the lifetime of the loop. So what's the effect of these kinks on the gravitational waves emitted by the network, and are they observable? In fact, it's slightly tricky to work that out. It's straightforward to find the amplitude of a gravitational wave burst emitted from a single kink on a single loop, but then you need to propagate those gravitational waves in the background space-time, include the effect of all the kinks on a single loop, which we modeled by this number k, or k prime, which can be as large as 10 to the 6th, and then include the effect of all the loops in the network. So thankfully, the process has been explained very clearly by Demel and Vilenkin. But then there was one new free parameter we had to introduce. We just don't know how many of these loops there are in a network of strings with junctions. Okay, and for me, I would really like to know, so it's a question for people who do simulations, do you see any number of these loops with junctions, and if so, how many? So we added this as one new free parameter, Q. The number of density of loops with junctions, we said, was a Q times a multiple of the number density of strings of loops without junctions. And we assumed that there were k prime kinks on these loops, which could be as large as 10 to the 6th. And for all our calculations, we in fact assumed that the combination of these two things was a very large number. So then is it observable? Unfortunately not, probably. In fact, all these loops emit a number of bursts, but if there are too many bursts, they actually overlap. So you can't resolve them separately. Many overlapping bursts just sum up to give a stochastic background. So the more kinks you have, presumably the higher the stochastic background of gravitational waves emitted, but each individual burst you probably won't be able to resolve it anymore, especially if this combination of parameters is big. So, not so clear. Let me get to my summary. So for network evolutions, it seems to me an important question is, are there loops with junctions in these networks? If so, what's their lifetime? We actually assumed it was of the order of 1 over the typical length scale of these loops, which is perhaps not very realistic. Another important question seems to me, if there are many kinks on these loops, they're going to emit many lots of gravitational waves, so presumably back reaction is going to be important. Is that the case? And the other thing which I think still needs to be addressed is the dependence of the scaling solution on the intercommutation probability. So that seems to me to be less well known. And then finally, I just want to mention briefly something about field theory analogues. So one field theory analog was U1 strings in the deep type 1 regime, where you can have junctions. You can have strings in a U1 cross U1 model. Junctions, sorry. You can have junctions in non-abelian string networks. What happens if there's a current on the strings when they meet at a junction? That's something which I've been looking at recently with Brandon Carter. It's complicated. And I would also like to say that in one of these models, at least this one which I worked on with Ed Perpland and other collaborators, we did notice that there can be spontaneous junction creation when the loops evolve. So the number of junctions doesn't always seem to be a constant. So that seems to me to be something interesting as well. Thank you.
Any questions for Danny?
If you have a current going into the junction, does the current propagate or does it push the string back? Or do you not know?
Both, I think.
Oh.
Yeah.
Disconnect.
So, also can it destabilizes the byte of down stick?
Yeah, I imagine.
Yeah.